Good morning and welcome to this morning's webinar. Could somebody just raise their hand or shout out just to make sure that you guys can all hear me? Excellent, thank you very much, John. Right, so today's webinar is about is a part of our SolidWorks in Your Industry series, part 10, lighting design. So let's get started. So, lighting design. What am I going to cover today? Well, I've had a look at the names of the people here, and I can tell you, you are all better at knowing what lights do than I am. So what we're going to be covering today is more sort of how SolidWorks ties in with other bits of lighting design. The situation I'm going to be looking at today is going to be sort of looking at a cast body and working out how we can improve that cast body for the casting industry rather than just for the design point of view, and also from a thermal point of view. So let's jump into SolidWorks. And here's my very simple light. Essentially consists of a cast, or what we're intending to cast as a body, a fascia plate which holds 5 LED lights in this example, and then has a glass fascia on the front of it. So let's go and have a look at the case. Looks everything in the world like a flower pot, I have to confess. So very simple. I've done very little on the inside. We've got mounting points on the edge here, and then we've got a surrounding sort of the case element of it. Now, as I said, the intention would be that we're going to cast this. So what we want to do is first of all have a quick look at it and see what the draft is doing. Draft is very handy if you guys as the original designers can put it on rather than your mold manufacturer. It gives you control over the model, so you know exactly where the draft's going to be. Potentially also saves them time and therefore you cost. So what we want to do is have a look at the draft analysis. Unfortunately, for some reason, when GoToWebinar is running, this button doesn't do anything, so I'm going to have to get to the button in a slightly different way. So please just bear with me as we bring that up. Right. So what happens here is we've got draft analysis using the front face as what's going to be our parting surface if we went on and we're going to mold this. So the red faces are those with what's called negative draft. The green faces are those with positive draft. Depends entirely on which way you can say you're going to pull it out of the mold. The important ones, as far as we're concerned, are the yellow faces and the blue faces. Blue faces are straddle faces, so they are both positive and negative. And in this case, we've only got the blue faces on our mounting holes. Those probably would be machined post-casting, so we're not going to worry about them. So it comes back to the yellow ones. These are either faces that have no draft on at all, or do not have draft of a great enough value to meet our required draft angle, in this case 3 degrees. So what I'm going to do is I'm going to come out of the parting line feature. When GoToWebinar is not running, the draft analysis button allows you to hit this tick and keep these colors visible, so as you update things, everything updates with you. So we're going to have to come back into this parting line in a second. So I've got a series of draft features here which I previously created, and we're just going to unsuppress, but I'm going to explain what I did. So this was a neutral plane draft using this surface as the neutral plane through 3 degrees on this outer surface. So it brings the mounting points in at a slight angle and this in at a slight angle. So if we come back to the front plane, you can now see these are slanted. We then need some more draft. So if we unsuppress that, and this is draft for these faces here, so either side of our mounting point. So if I go to that one, we can now see these are at an angle. These were done using what's called a parting line draft. So let me just edit that and we'll have a look at the features. So chose a parting line, direction of pull, so which way it should be turning, whether it should be pulling in or out based on this face up here. The parting lines are these edges, and I could select all 4 of them in one feature, which makes my life a little bit easier. And the only other button I had to click was this other face button, so that this yellow arrow is pointing in the right direction. Otherwise, it tries to draft this face as opposed to that face. and then we can do all of them in one feature, which does speed things up. So now it's drafted correctly. If I came back to my mold tools, let's give my machine a couple of seconds to catch up. So if I come back and we select that face and 3 degrees again, reason I chose 3 degrees, it's large enough for you guys to see on screen more than anything else. So hit the draft analysis. You can now see all of that is red, so everything beyond my selected face is red, and everything on the other side of my selected face is green. So I'm now nicely split up, and a mold maker would be very happy with you. The exact angle that you would want to use would depend both on your tool maker, your mold maker, and on the requirements of your part. Now, something else to consider when molding is sharp edges are generally frowned upon. So I've got a nice sharp top to my flower pot case. Not something that tool makers want, particularly if you're expecting to make many tens, hundreds of thousands of them, because sharp corners are the first things that wear away. Now, in some situations, we need to keep our sharp corner, and it would be an inspection point. So, for example, on this front face, we want this nice sharp corner because that's what the glass mates up to. But for everything else, we want to try and fillet away as many of the sharp corners as possible. So we have a fillet that goes on. Now, something to note, although I have filleted a lot of edges, I only need to make 2 selections. One of which is this face, which then does all the edges related to the face. The second, by right-clicking on this edge, and I'll just do it again. By right-clicking on this edge, I can choose Select Loop. And what happens is it will then go all the way around and create a loop for me. So again, ways to speed up your modeling and mean that you have to make fewer clicks to get the result you're looking for. Again, I've chosen 3 millimeters for my radius just to match with my 3 degrees. Some new stuff in 2014, we've got both circular and conical fillets available now within the fillet tool. I'm sticking with the circular fillet, but if you need conic fillets, they are available. Generally, they're there for aesthetic reasons, or people want to use them for aesthetic reasons. It sort of enables you to square off your fillet, for want of a better term, but it can give you some quite nice image or quite sort of friendly fillets rather than what can be quite abrupt with the circular ones. So we're going to accept all of those changes, and I need to unsuppress that as well. So we'll put my fillet on. So I've now completed the changes I want to make to my case, and we're going to go back to the top level assembly. Now, before we go any further and start having a look about how this design works with the heat that my LEDs are kicking off, I just want to mention something else. I've left this all as a steel effect because I think it's going to look quite nice on my finished light. But the LEDs, you'll notice here, are just showing sort of a paler grey. What I've done for the LEDs is I've actually applied an appearance to them of white LED. Now, why might I do that? Well, in the background, I've got a render preview previewing up, and you can see that my LEDs are actually glowing. So by applying the white LED appearance to the LED section of my light, I can improve or start to add detail to my my renders, my marketing documentation, just so people get an idea of what's glowing. Now, I could increase the intensity, which give you a much better idea of what's happening with this particular light, but just as a guide, just to show you guys what you can do with the appearances as well. Right, I'm going to close that and give my computer a break. So what we now will need to have a look at is applying simulation to this to see what's going on. So we come and we start a thermal study. Now, those of you who have been paying extra special attention may have noticed that in my feature tree I've got a lot of parts for what is such a simple model. Now, I've got my case, I've got my fascia, which is sort of the holding plate for my LEDs. I've got the glass on the front, and I've got my 5 LEDs. I've also got this thing called case air and LED air. Now, each of the LEDs is open-fronted at the moment in my model. So there's an air gap between the actual LED bulb and the glass front plate. Now, for simulation or for thermal simulation to work most effectively, we need to create a body in that empty space and give it the properties of air. So I've said these ones are air. The same happens for the body behind the drivers for the LEDs within the case. So again, I'm creating a case air, and if we chop that up, you can see I've got this big empty void in the back here, and what I'm doing basically is creating a body that fills that in, just so that I've got something in that space to conduct, and it will use the properties of air to do so. So what we're going to do is look at simulating this. So I've applied the SolidWorks materials air, and then I've applied to everything else. I've said it's either cast carbon steel. I've said my LEDs as a mass are an aluminium. Essentially, I'm doing that in this particular webinar just for simplicity. Just said the whole thing is aluminium. If you have a better idea of the properties of your light body or your LED body, then you can apply more accurate properties to it. But as an entity, aluminium seemed to make sense to me. So what did I do next? Well, because it's thermal, just a quick note, thermal is available in SolidWorks Simulation Professional if you guys want to use it. So as well as having parts, giving them materials, I don't need to apply any contact. Everything is assumed to be bonded, i.e. my air touches my LEDs, my air touches my case, and therefore we get conduction between the two. First of all, I needed to apply heat power. So this I did to the back of my LED bodies and just said this is the driver area of my LED, and therefore is the bit that's going to get hot. I've got 5 of them. I actually want to make them 60 watts each. So what I've done, because I've got 2 faces each, we say 300 watts comes out of all of those faces as a total, essentially 60 watts per LED driver. So we can accept that. And I'll turn my case back on. So I've now got my source of heat in my model. We then have convection, and we're going to edit this up. And what happens is this essentially is all of the faces of the external faces of my model. And because we just applied the fillets, we can go along and we can just select those additional fillet faces that weren't previously included. I'm not selecting the holes because in use they will have a bolt in, so it doesn't seem to make sense to select them as well. The convection coefficient is selected for what's called free air. So my body or my model sat in air is going to be saying that. If you go and have a look online, they reckon the convection coefficient for free air varies between 5 and 25 watts per meter squared Kelvin. Now, I've chosen 12 as being roughly in the middle. That varies based on humidity, whether there's a lot of air that can move around or only a little bit, whether there's any particulate matter in the air, and so on. So generally, unless you have a much better idea of the actual location the light's going to be used in, picking something in the middle of the range is not a bad move. And then the next step is bulk ambient temperature, i.e. what is the air temperature that we are sat in. So what I've said is 285 Kelvin, so roughly 12 degrees Celsius, which is England most days of the year. So we'll accept the convection. I then have a radiation, again from all of the same faces as the convection. So we're going to accept the extra faces for the fillet. Oh, not the edge, we want the face. So again, and now what happens is we say, what is the temperature? 11.85. I'm just displaying this one in Celsius. That is 285 in Kelvin. And then we have the emissivity. Now, again, you can go online and find tables and tables of general emissivity values for particular materials. Emissivity depends on color and how shiny something is. And this is a value for steel. We then have another radiation value for the glass on the front, set up in exactly the same way as the other radiation, but with a different emissivity value, and this one's for glass for obvious reasons. And that's the setup of this done. Now, the next step would be to mesh it. As with all meshing, you ideally want to have at least 2 elements per thickness. Now, this is mostly pretty chunky, so we don't have to worry too much. We can just use the standard mesh. So I'm going to click Run to let it mesh it and run the simulation at the same time. Something to be aware of, the more detail you put into a model, so I've added the fillets, we've got small features and so on in the LEDs, but the more detailed you make the model, the longer the solving will take and the finer the mesh will have to be. This should take, he says with great confidence, about 1:20 to do. So if we just sit and watch this for a second or two. Teases you by getting to 90% really quickly. Okay, and now that's finished, what we're going to do is we're going to get a display of temperature across my model. Green is hotter, blue is colder, and if I just move that out of the way from my end, we vary between an absolute maximum temperature of 444, which isn't on the outside, it's on the inside, and a minimum temperature of 324. So these blue sections are actually still north of 300 degrees Celsius. Not great as a model. I've either crammed too many LEDs in, put LEDs of too great a power in. To see the full maximum temperature, what we're going to need to do is clip this. If I do it on that plane and then hit the tick. So now we can see we're sort of getting a section through our heat plot, and you can see, as it's not too surprising, the body, the driver of the LED is the hottest section, so that is where our 400 degrees is. So I've either got some pretty brave LEDs or I'm going to need to do some work on the design. So we can have a look at these models now. So what we want to do is try and improve the cooling effect of our case. So this is where we come to our next model. So if I jump across to light version 2. So exactly the same principle, but you can see what I've done is I've added some nice fins to the back, rounded them off so you can't see them when you're looking at it from the front, and then we've gone through the same process of improving things for molding. So if I just open that up, the significant changes are I've got this where we've then patterned it and mirrored it, so I've got them on both sides. What I've then done is, again, looking at the drafting element to try and make sure that this is going to come out of a mold, we've gone through a draft. So if I select that edge, we've got, I've gone and selected the wrong edge, excuse me. That's come out. No, it's still wrong. I've still got the wrong edge. But it gives us an idea. I just want to try and explain where the colours are. Unfortunately, I had to do I've had to swap how I've had to do this for the webinar. So what happens is I added a split line all the way around my model, including the inside. And the idea behind that is that enables me to think about molding it. Now, the last one, we said we were going to take this as the parting face, so where the mold would join up, and we'd take it off that way and come out in the middle. Now, for this model, that doesn't really work because we've got all of these fins, so it makes life a lot more difficult. So what I actually decided is we would have our mold going this way, so hence the split line. So I split it all the way around, and we would then have a core which would go into the center, and then we'd have a top half and a bottom half of our mold. This makes it much easier to draft the fins up. So we added draft because we've got that split line to the back face, so that's going to come out of the mold nice and easily. We then drafted this edge here, and the matching one of those is that edge there, so that comes out of the mold nice and easily, so this doesn't. We have again maintained this as flat because this is essentially a visual edge and it's what the glass is going to adhere to. Now what we need to do is draft the fins. To do that, I created a plane at the top, and then we applied draft from that plane coming out onto these fins. Again, all of this was at 3 degrees. The only face that I haven't applied that draft to is this face here, and it's partly because 3 degrees means it comes over center. So I could have had 2.5, for example, but also partly because it's the outside fin, it's going to be the easiest thing to remove from the mold. So we can sort of accept that difficulty, or we could accept a reduced angle of say 2.5 rather than 3 on that face. So we've applied draft to all of our faces as before. Again, we haven't done anything about the holes because they'd be milled afterwards, and so we've got a completely different molding methodology. Now, if we have a look at the back, our fins are getting fatter as they come down. Now, that's partly because of the draft requirements, but also from a thermal point of view, the fatter something is, the easier heat travels through it. So at these points, we're pushing the heat through faster than at these points. Now, these outside edges would hopefully be colder, but this shape allows us to force the heat through faster. The theory being that it enables us to get heat out of the main body of the case, the sort of flower pot shape, into the outsides of the fins where it can cool and get away. So I'm going to close that without saving changes and get back to my model. And what we're going to do, these colours have come through from the draft analysis previously. So we're going to have a look at how this simulates. Now, this one takes quite a bit longer than the other one. Now, because I haven't added fillets to it, it's not as bad as it could be, but obviously we would want to go through and have a look at fillets for the same reason we wanted to have a look at fillets for the previous case, because they're going to make it easier for the mold maker and make the mold more durable for producing more parts. But for simplicity within the simulation, what happens is I ignored them. So we went through, we added heat power, exactly the same as before. I added a convection, same principle, but a load more faces to select. I added radiation, again, a whole load more faces to select, and then we've got the radiation for the front. Now, that gave us a thermal result. Now, from the outside, it looks pretty much the same. We've got some cold spots on the front, and the back is blue. So compare that to our previous display, and it looks nearly identical. I think there's a slightly better gradient of colour. The other one was a bit sudden. But beyond that, it doesn't seem to have done much. Now, that's one thing to be aware of when doing simulations, is the colour is related to our graph. And if we have a look here, maximum temperature is 291. So we've cleared about 150 degrees out of our case and reduced the temperature of our internal components by 151 degrees by adding these fins. So we can see that the concept I had with those fins is pretty good. However, outside, coldest bit of the case is 174 degrees and still slightly burny if you touch it. So we would need to potentially now either look at further fins, maybe make the fins fatter, spread them out a bit, maybe have fins coming out of this side section, or have some way to conduct heat from the back of the driver. So again, if I come through and I put some section clipping on this so we can see inside, we again have got an airspace in the back here between the back of our case and our drivers for our LEDs. Now if I found some way to conduct heat more directly from the drivers to the back of the case, I could potentially improve my cooling further. This section at the back is a lot cooler than the section at the front, so therefore could take more heat if I could get it there. But air being not a great conductor, it's not travelling. So potentially I need to do some design on the inside of the case to take heat from the back of the drivers straight through. So potentially, as well as a route for cabling in the back, which the sharp-eyed among you may have noticed there isn't any yet, but as well as that, potentially I could have some metallic heat conductors coming through into, or much nearer the centre of the body and to the touching the drivers, to conduct heat straight to the back. Now if I could do that, potentially touch the back of the drivers as well, then it enables me to conduct heat much more effectively out of the back of the case. So we can see very quickly with SolidWorks thermal simulation that we can test design ideas, potentially improve designs very quickly. So I can now go back in, model up some different fins, come back in, simulate it, and the simulation for this one takes approximately 1.5 minutes, the same as the other one, because there are no fillets on it. But we can test new design ideas for cooling methods for LED lamps very quickly without having to make any up, do some testing, go back, try again, because although these would be cast in the end, we're unlikely to cast them for the first off prototypes. They're more likely to be machined, time-consuming and expensive. So being able to test at least 3 or 4 designs and pick the best of those is certainly going to make our lives a lot easier. We can also see that my aim to have 5 LEDs in this is probably somewhat over the top, and I'm likely to need to drop 2 or 3 of them, or change the power of the LEDs. So we were looking at 60 watts of heat coming out of the back of these. For an LED, heat conversion is pretty significant power in to heat out. So we're working on theory of having roughly 60 watt LEDs. If I drop these down to maybe 30 watt LEDs, so halved it, we're going to have a lot less heat, and we can see produce, so we can see what the heat of the body in the case is going to be like. Now, other things we can do with simulation is have a look at heat power out of things. So as well as looking at the temperature display, what we can do is we can choose to probe something. No, whoops, I've got to right click in the right place. So if I choose to probe this, I can choose to probe a particular node, and we can get the temperature at that exact point. But as well as the temperature at that exact point, we can then start to use this to get other values out. So we can start to graph across a line, for example. So if I clear the selections and I took that line, we can start to, or take several points, for example, we can start to graph across it. So because I've got my split line, we can get some nice values along my split line. So if I take a point here, a point there, a point there, we can come in, and if I move that out of the way so I can see what I'm doing, we could start to take a number of points along my split line, and then we can ask it to graph them. So we can see the temperature between the front and the back of our model. We can see how that's dropping off. These numbers down here are the node numbers. They are essentially meaningless. It's just how SolidWorks has broken up the model, but to a user getting temperatures out there are just positions. So we've got temperature against the node number there. So we can start to get more information out and take this on for other tasks. So potentially we can see the heat out of here, which would enable us to tell what's happening with the frame that this might be attached to, for example. We could take our model further again, and we could start to model the brackets on and then see what the heat conduction is, so the temperature on the bracket, heat conduction from our lamp to our fixing assembly, and we can sort of move on from there. So we can very quickly start to see how our heat, not only is it going to affect it to touch, but how it's going to affect it to other environmental factors and other model items. So thank you very much for watching. If you've got any questions, ask them now while I continue talking. We've got some more webinars coming up. Next week we've got SolidWorks Simulation Trace Path. For lighting designers, I'm not quite sure how useful this will be, but do feel free to come and have a look. It's got a lot more to do with moving items within simulations and seeing what shape cams and things should be. The week after, we've got another SolidWorks in Your Industry webinar on agricultural machinery. And on the 27th of February, we have eDrawings Explained. So it's going into a lot more detail of what eDrawings is, how you can get hold of it, differences between eDrawings and eDrawings Professional and what those benefits are and so on. So thank you very much for watching. If you think of any questions in the near future, feel free to get in touch with us on the support line at the bottom of the page or drop us an email. Thank you.